Hello everyone, thank you for watching this video. Today, we'd like to introduce a generalized two-stage framework for practical plant disease diagnosis. My name is Hitoshi Yatomi from Hosei University, Japan. First, we'd like to introduce the important prerequisite of this study. There have been many automated systems for plant disease diagnosis and reported very high diagnostic performance, such as 95% and more. However, most of those studies applied inappropriate data splitting, that is training dataset and evaluation dataset is inappropriately separated. Recently, so many recent studies indicated those real performance of those systems must be much lower. That is, this figure illustrates this issue. Usually, the images taken by some farm fields has shared geometry, background, digital cameras, and subjects. In such a situation, a similarity of those images, each images, are very high. In such a situation, if we split the training images and test images by stochastic way or applying just conventional cross-validation strategy, it has the test image, the model. If here, for example, this is a test image, but the model is already trained very similar images. So that is the eventual data leakage has occurred. So that is why the actual model performance is much lower than reported. So recently, the study with large dataset, 220,000 images, has revealed that even with the using the sophisticated CNN models with appropriate data augmentation technique, those models attained only 67% for crops diagnosis in macroF1. But if we use same dataset with evaluated with conventional 5-fold cross-validation, the diagnostic performance is almost 99%. But apparently, this is inflated and inappropriate performance, and real performance is this 67%. In this evaluation, test data is collected different field than the training data. That is rigorous evaluation. The reason of those limited true performance is ultimately caused by insufficient diversity of training data. This is typically explained with large domain gap. Here is examples. Those two images are example of bacterial spot. Here is taken in Nagano prefectures, and this is captured by different Ibaraki prefecture. The appearance is much different. Here, this image is looks similar to this one, but quite similar, different disease, but quite similar appearance. This is a difficulty caused by domain gap. To overcome this problem, collecting more image is important, but usually difficult. So data augmentation and data generation is a good way to overcome this difficulty. And also, CNN or vision transformer, our image classification has a vulnerability to variation in subject distance. For example, here is a cucumber leaf infected by CCYB or MISV viral disease. So when the target test image is captured as similar to training data in terms of the shooting distance, the model provided reasonable outcome, correct diagnosis. But even the same target, but different distance, the model yielded wrong diagnosis. This is evidence, one of the evidence that the CNN bit classifier has a difficulty to handle the variation of the target. On the other hand, object detection-based methods such as YOLO V5, 6, 7, and like that, those techniques have several advantages to CNN or bit-based models. One is a robust to distance variation, can detect tiny regions such as initial symptom of powdery mildew and like that, and capable and provide the location of lesions. On the other hand, those models require very expensive annotation and tend to show the low detection performance for viral disease. So viral disease shows subtle symptoms throughout the target. So those object detection model has difficulty to detect this one. And also, since object detection model cannot train the healthy cases, that is no boundary boxes cases, cannot train those cases. So using object detection model, so many false positive when we evaluate the healthy cases. That is a problem. In change world, classification model and object detection model each have different strong strengths and weakness. So here is a preliminary result of preliminary experiments using EuroB7, one of the cutting-edge object detection models. Even with 20,000 training images and 290,000 annotation box, but this model showed insufficient classification performance due to the preceding reasons. So in this paper, we propose effective and generalized two-stage framework for plant disease diagnosis called Hierarchical Object Detection and Recognition Framework, HODRF. The proposed framework is composed of two stages. The first one is ROI detection, so using object detection models. Then the following stage is diagnostic stage, using classification model, using like a CNN or vision transformer. So since in the ROI detection stage, the only one class detection, so detection regardless of disease type, we detect the lesion regardless of disease type. So object detection model can detect even minor symptoms, a smaller number of symptoms. And also, thanks to two-stage architecture, the false positive can be addressed at the latter stage. And also, this in this framework determines ROI like this by detected region. And for each ROI, the following classifier identify what is it. So since ROI is specified, the distance variation is reduced, and we expect the following classifier will provide better performance. And finally, the final diagnosis is determined by majority voting. So this increases the model robustness. Here, we conducted experiments using total of 281,000 images, in which 240 for training and the rest for testing. These images are collected 27 farm fields. And for implementation, we use the EuroB7-W6 as an object detection model, and pre-trained efficient V2 pre-trained with image dataset as a classification model, and augmentation and optimizers are shown like this. Here is an example of detection results. Here is the result of efficient V2 CNN, and this is the object detection model, EuroB7, and this one is proposed. As we can see, here is a healthy eggplant leaf, but we can see the EuroB7 misidentified as bacterial wilt. This is a common tendency of false diagnosis, a false positive, due to one of the limitations of object detection model. And here is a cucumber infected by corynespore leaf spots. So the CNN overlooked the symptom and recognized as healthy. But the proposed method successfully identified the disease type correctly in all these cases. Here is a summary of the results. The proposed HODRF outperformed EuroB7 by 6 to 21 points on healthy data diagnosis. And generally, the proposed framework showed 4 points in average to EuroB7 and 3.4 points for better performance to efficient V2. Those very good performance is obtained by the effective integration of object detection and classification models. So here is the reason, the summary of reason. So our framework performed one class detection. So as I mentioned before, so our object detection model can detect the even minor symptoms. And two-stage architecture can overcome the difficulty of OD. That is, the OD is very difficult to handle, diagnose the healthy cases. And ROI-based classification help to diagnose the symptom with per image classifier such as CNN or BEAT. And also, final majority voting increase the model robustness. As a conclusion, in this paper, we propose effective and generalized two-stage diagnostic framework for plant disease and demonstrated its effectiveness with large-scale data. So also, we need to address the large domain gap caused by insufficient training dataset, but this can be addressed with more sophisticated data augmentation or data generation, such as GAN-based method or diffusion-based methodologies. Thank you for kind attention. Our papers can be found from these links, and we also publish so many plant disease and plant pest diagnosis, and you can find the publication from this link. Thank you very much for kind attention.